In the world of software, there are a few core ideas that can literally be the difference between a project that's a joy to work on and one that just becomes a tangled, frustrating mess. They're called the solid principles. And in this explainer, we're going to break down exactly how these 5 concepts can help us build software that's built to last. Oh, you know the feeling, right? You go to change one tiny little thing in your code, and suddenly a dozen other things just break. It's like pulling on one thread and watching the entire sweater unravel in your hands. Well, that brittleness, that fear of even touching the code, that is exactly what the solid principles are designed to fight against. And this really gets to the heart of it all. On one hand, you can write code that's like modeling clay. It's all mashed together, and any little change just makes a huge mess. Or you can build with Legos, using strong, modular pieces that snap together cleanly, and most importantly, predictably. Think of Solid as the instruction manual for building with code Legos. All right, first stop is the S, and that stands for the single responsibility principle. And honestly, if you only remember one of these 5 principles, make it this one. It is the absolute foundation for everything else we're about to talk about. Okay, so the official definition, a class or function should have only one reason to change. It sounds a little academic, I know, but it boils down to something incredibly simple. Every piece of your code, every single class, every function should have one job and one job only. That's it. So this probably looks pretty familiar. I think we've all seen or maybe even written a class just like this one. This single user object is trying to be a data holder, a password manager, an emailer, and a database handler. It's wearing way too many hats. So what's the actual problem with that? Well, here's exactly why it's a problem. Let's say you need to change how emails get sent. You have to go digging around in the user class. If you decide to switch your database technology, yep, you're right back inside that same user class. You have multiple, completely unrelated reasons to change the exact same piece of code, and that is where the risk of breaking things just skyrockets. So the solution is simple. We break it up. We create these small, focused classes. Now, the user repository only cares about the database. The auth service only cares about security. If the email API changes, you only have to touch the email service. Everything is isolated, it's safer, and it's so much easier for you or anyone else to understand. Okay, so now we have our small single-purpose blocks. The next 2 principles, O and L, are all about how we connect them, how we plug them together in a way that's both super flexible and totally predictable. Now this one kind of sounds like a riddle, doesn't it? How can something be open and closed at the same time? Well, what it means is that you should be able to add new functionality to your code without ever changing the existing working code. No more risky surgery on classes that you thought were done. And here is a classic example of breaking that rule. This payment processor works just fine, but the second your boss asks to add Apple Pay, what do you have to do? You've got to crack it open and add yet another if statement. Every single new feature requires modifying the core logic, which is always risky, and it just gets messier over time. And here is the magic. Instead of changing that original code, we introduce an abstraction. Think of it like a universal plug that any payment method can fit into. So now, to add Apple Pay, we just create a brand new class that fits that plug. The original payment processor doesn't change one bit. It's closed for modification, but it's open for extension. See? This brings us right to the Liskov substitution principle, or L. And this famous quote, it just perfectly captures the whole idea. It means that any child class you create must be a perfect substitute for its parent class, without causing any unexpected, nasty surprises. Now, this is the most famous example of where this idea can go wrong. I mean, in geometry, a square is a rectangle, right? So making a square class inherit from a rectangle class feels totally logical. The square class just has to make sure its width and height are always the same. What could possibly go wrong? Uh-oh, indeed. A function that works perfectly fine with a rectangle object suddenly breaks when we substitute in a square. But why? Well, it's because the square changed the rules. It violated the parent's contract, this unwritten rule that setting the width and the height are 2 separate things. Our substitute duck didn't really behave like a duck, and our program got the wrong answer because of it. So we've got our small building blocks. We know they need to be perfectly substitutable for one another. Our final 2 principles, I and D, are all about designing the connections between them in the smartest way possible. In simple terms, this really just means don't create fat interfaces. Make small, focused contracts instead. A class shouldn't be forced to implement a whole bunch of methods it has absolutely no use for, just to satisfy some bloated, oversized interface. And this is a perfect illustration. If we have one big worker interface, are human workers totally fine? But just look at the robot worker. It's being forced to have eat and sleep methods that do absolutely nothing. It's awkward, it's clunky, and it's a clear sign that our interface is trying to do way too much. The solution? Split it up into smaller role-based interfaces like workable and eatable. And that brings us to our final principle, D, for dependency inversion. In this analogy, it's the key to everything. You don't wire your light switch in the wall directly to a specific brand of light bulb, do you? No, that would be insane. Both of them connect to a standard socket, an abstraction. This visualization shows that shift perfectly. On the left, a report generator is hardwired directly to a specific MySQL database. But on the right, we've inverted that connection. Now, both the high-level report tool and the low-level database connect to that universal socket in the middle. And what that means is we can just unplug MySQL and plug in a completely different database without ever having to change the report generator itself. That's powerful. Okay, deep breath. We've covered all 5 principles. So the big question is, how do they all fit together into a single, cohesive philosophy for writing better code? So here's a quick recap. And if you look closely, there's a common thread that runs through all of them, and it's this: the effective management of dependencies. Bad software is just a tangled knot of dependencies. S, I, D, and I, they help us create small, independent building blocks. And O, L, and D, they help us connect those blocks with flexible, abstract sockets instead of hardwiring them all together. Ultimately, SOLID is a strategy. It's a strategy for dealing with the one absolute, undeniable constant in software development: change. Following these principles helps you build systems that are resilient, that are adaptable, and frankly, that are just way more pleasant to work on. It really all comes down to this. We know our code is going to change. The only real question is, will it be ready when it does?